Hello students, I am Dr. Rajaram Dhok from Savitribai Phule Pune University affiliated Agricultural Development Trust Shardabai Pawar Mahila College Sharda Nagar Baramati. Let's start. Ionic Solids Lecture 7 Radius Ratio Effect. So in this lecture we see the what is the effect of radius ratio on the stability of complex and on the shape of the ionic solids. The ratio of the radius of cation to that of the anion, that is called as radius ratio. So simply we can write this radius ratio by equation radius ratio is equal to radius of cation divided by radius of anion. Usually the radius of cation to radius of anion is less than 1 because size of cation is smaller than the size of anion. So radius ratio is very important in determining the coordination number and the geometry of the ionic solid. So this radius ratio is useful because from that radius ratio we can get the coordination number of that cation anion and also the actual geometrical shape of that ionic solid. And so that is very important. The effect of this ratio in determining the coordination number and shape of an ionic solid, that is known as radius ratio effect. So here we see the radius ratio effect by using certain examples, by taking the certain examples. So we consider the general example Ca. So we consider crystal Ca. In that, C means that is the cation which carries positive charge, and A means anion, it carries negative charge. So cation C plus are immediately surrounded by anion A minus, and anion A minus are again immediately surrounded by cation C plus. So this is continued in all the three dimensions and it forms a long crystal structure in that cation plus anion minus cation plus anion minus, this structure is regularly increased. The number of immediate oppositely charged neighbors, that is called as coordination number, and already we have discussed this. So in this example you see that this center there is one cation and that cation is surrounded by 6 number of anions, and so this cation is surrounded by 6 anions, so coordination number of this cation is 6. In a binary compound, we take the binary compound Ca, in that NaCl is one of the example. So coordination number of cation and anion is equal. But there are some other compounds in that ratio of cation anion is different. We take the Ca2 types. In Ca2 types, there is example of CaF2. In that one cation, they are surrounded by 2 anions. So in that the coordination number of cation is double that of the anion. And the arrangement of ions in an ionic crystal depends on the relative size of cation and anions. The increase in the radius ratio increases the coordination number of cation. So ionic compounds having the coordination number C plus is 3. 3A minus ions are attached to the C plus when there is coordination number 3. So that C plus is surrounded by 3A minus ions, and A minus ions are immediately surrounded by 3C plus ions. So in this case, such compounds are planar triangular arrangement, and such structure is quite stable because the cation and anion is immediately in contact with each other. Attractive force and repulsive force between cation and anion is equal. So such type of structure we see here. Now we see here the A structure. In this A structure, cation is touch with anion. So in all the three cases, cation, anion touch. But anion and anion, they are not attached with each other. So in this case, here attractive force between cation and anion is more. But anion repulsive force is less. And because of that, here attractive force is more than the repulsive force. So this is the stable structure with coordination number 3. But in this case, there is one other problem, that when cation and anion attach with each other, surrounded with each other, then in that case, close packing is not observed because here space is observed, void is observed, and this structure may be defective. Now we see the second case, B case. In that, cation is at the center and anions are surrounded with this. Now we see in this structure, cation touch with anion. So all the three anions are touched with cation. Also anion attach with each other. Means here cation and anion is maximum close with each other, and here attractive force between cation and anion and repulsive force between anion and anion, that is equal. And so this is a limiting case, or this is the ideal case, or in this case there is stable structure for coordination number 3. Now we see the third case. In that, cation size is very small, so cation not touch with anion, but anion touch with each other. So in this case, here attractive force between cation and anion is less because they are not touched with each other. But anion have the repulsive force. So in this third case, here attractive force is less and repulsive force is more. And so here unstable structure is formed. So this type of structure has more unstable, and that is not stable structure. And so out of these three cases, the B case is the ideal case, or that is the general case, that is the limiting case, and this is stable structure. But A and C are not the stable structure. So here, if we see the geometry of these structures, then we can calculate the geometrical phenomena, that in the limiting case, Ra minus divided by Rc plus Ra is equal to cos 30 degree, and that is equal to under root 3 by 2. So Rc by Ra is equal to 0.155. So you see again the same structure we have shown by some large size. Here this is the cation, these are the anions, and here their geometry is shown. Now we see here, if we see this distance, then this is the radius of cation. This distance, this is the radius of anion. And when that radius of cation and anion are added, then we get this internuclear distance d. Again you see, this is the angle, this is radius of anion, and this is the one distance. So in this way, we can calculate that, and from that we get the geometry of these compounds. So in this case, here radius ratio when falls below 0.155, then C plus becomes still smaller, and then structure 3 will be formed. And so this is the not possible, or it is unstable structure. Here in this C structure, cation is not touching with any other ions, and already we have discussed that point. Now we see the structure in coordination number 6. So in coordination number 6, one cation is surrounded by 6 anion, or one anion is surrounded by 6 cation. So firstly we see this A structure. Here at center there is cation and they are surrounded by 6 anions. Now we see the second structure. Here the one cation is at the center and they are surrounded by 4 anions. So actually in octahedral structure, 4 anions are in the plane and 2 are in the pyramidal position. So this A structure we can show in the same way in the octahedral position here. So this B is limiting case of Ca. In that C plus that touch to the all the A minus ions. And here the cation and anion attractive force and repulsive force are same. So in this case, radius of cation to anion, or radius ratio of cation to anion, that is equal to 0.414. Now we see this C case. In that, cation size is smaller and cation not touch with anion. So here attractive force is less and repulsive force is more. And so this is the unstable arrangement, and in that unstable arrangement, radius ratio of cation to anion is less than 0.414. And so this step decreases the stability of that compound. Again, we see the D case. In that, cation size is larger. So here attractive force and repulsive force, that is not same. Here attractive force is more and repulsive force is less. So this is also the unstable arrangement. In this case, when we see the radius of cation to anion ratio, then it is greater than 0.414. So if we see this all the cases, then in that P case is the limiting case, and in that stability of the complex is more, and in other case stability of the complex is less. So we see the geometry in this coordination number 6. So here radius of cation to anion, that is equal to cos 45 degree. We solve this RA divided by RC plus RA, that is equal to 1 by under root 2. So RC is equal to under root 2 RA minus RA. So by solving that, we get RC divided by RA is equal to under root 2 minus 1. Again, by solving, we get 1.414 minus 1, that is equal to 0.414. So radius of cation to anion here, that is equal to 0.414, and this is suitable for the B case. In case of the C and D, this is not suitable, and so B is the stable structure, or B is the stable arrangement, and C and D are not the stable arrangements. Now we see the one of the alternative method of calculating radius ratio for coordination number 6. So here you see this diagram. Here we have shown the cation. These are the anions, and these cations and anions when attached with each other, then we get the radius. So you see here at the center of that cation, we given the name to that point K. Again, center of anion, for one anion we have given the name L. For the other anion we give the name N. And these two are joined, then that point is M point. Now see here, this is radius of cation, means this Kn or this Kl, these are the internuclear distance. This Lm and Mn are the radius of anion. So from this triangle, if we see this KMN, then this is the right angle triangle. So Km is perpendicular to this Ln. Km is perpendicular to Ln. So we write Km is equal to Lm. Km is equal to Lm, and that is the radius of anion. So here we see that KML, KML, this is the right angle triangle, or KMN, this is also the right angle triangle. And for that, we write the equation KL square, KL square, that is equal to Km square plus Lm square. And so here by solving this, we get the calculation, and for that purpose we write KL square is equal to radius of cation plus radius of anion square is equal to Km square, means that is the Ra square plus Ra square, that is equal to 2 Ra square, or that can be written by rearrangement Rc plus Ra is equal to under root 2 into Ra is equal to 1.414 Ra. Again, we can calculate for Rc 1.414 Ra minus Ra, then Rc by Ra is equal to 1.414 minus 1, that is equal to 0.414. So for the coordination number 6, the lowest limiting ratio is 0.414. And so if we see these structures, that is the C structures, then here the radius ratio is less than 0.414. In the D case, radius ratio is greater than 0.414. In the B case, radius ratio is equal to 0.414. And so this B case is the stable state, and C and D states are not the stable state. So here different ionic crystals and their limiting radius ratios are given, and from that the particular shape of that crystal is observed. So in this table, here coordination number, limiting radius ratio and shape of crystal is given. So for the coordination number 4, limiting radius ratio is in the range of 0 to 0.155, and in that case shape of crystal is linear. In coordination number 3, limiting ratio is 0.155 to 0.225, and shape of the crystal is triangular. For coordination number 4, the limiting radius ratio is 0.225 to 0.414, and shape of the crystal is tetrahedral. Again, in coordination number 4, limiting radius ratio is 0.414 to 0.73, and shape of that molecule is square planar. Now in coordination number 6, limiting radius ratio is in the range of 0.414 to 0.732, and shape of that crystal is octahedral. Then coordination number 8, here limiting radius ratio is 0.73 to 1, and shape of that molecule is cubic. So you remember that for every shape, what is the limiting radius ratio and coordination number, or in that particular coordination number, what is the limiting radius ratio, and in the corresponding limiting radius ratio, what is the shape of that crystal. Now This radius ratio and shape of ionic crystal we see in case of the NaCl molecule. So we take the NaCl example, and according to that we see the radius ratio of that and what is the shape of that NaCl. So in case of the Rna, its value is 0.96. For RCl, value is 1.81. So by taking the radius ratio of this Na plus and RCl minus, we get the value 0.525. So this 0.525 value lies between 0.414 to 0.73. And here coordination number should be 4 to 6. So here we know that in NaCl coordination number is 6 and it shows square planar or octahedral shape. So X-ray study shows that NaCl crystal has an octahedral structure, and actually by calculation the shape of the NaCl is also octahedral. Then we take the second example, that is CsCl. So we see the radius ratio and shape of ionic solids in CsCl. In case of the CsCl, by calculation, we get the radius ratio 0.93. And this 0.93 are in between the 0.73 to 1. And for 0.73 to 1, the coordination number should be 8 and it shows cubic structure. So such type of structure is suitable for the CsCl. So that CsCl has cubic structure because its coordination number is 8 and its radius ratio is in the range of 0.73 to 1. In this case, ratio of cation to anion is also 1 as 1. So from this radius ratio, from this ionic solid, we can suggest the shape of that molecule.